Well, hello everybody. My name is Emmanuel Williams, and this is going to be a tutorial on the multiple expansions that are used in electrostatics. So, coming to multiple expansions, where do these things come from? Let's first look at or revisit the theoretical premise of this before going on to solving a few problems. Let's get started with the show, shall we? So this video is going to be on the theoretical premise of the multiple expansions. Due to some constraints, I'm forced to make multiple videos of the entire tutorial. So in case you guys are conversant with the basics and whatever that's about this tutorial, you're free to skip this video and look at the solutions to the problems in the subsequent video. Thank you. So this is how a charge distribution looks like in space. You have a charge configuration represented by rho, which is in a position vector r prime. Now, if there is no charge in outside a domain, I can simply define that by saying that rho is 0. So equivalently, I have a charge density rho, which is 0 outside a domain, and it's some finite quantity, or could be infinite, which is the Dirac delta function or something of that kind. So something of that sort will exist inside the domain in which we define a system of charges. Then you have the origin, and you have the point of interest, R, where you would like to compute the potential. So how do you compute the potential? Either you use basic Coulomb's law, where you take rho dV as a point charge and do stuff, or you derive the solution from Helmholtz theorem and stuff you already are very well aware of. So given that, we are left with this equation. So what we'd like to do is we'd like to break this in terms of potentials due to various configurations of charge. These configurations are called monopoles, dipoles, quadrupoles, octapoles, and stuff you can probably think of as we go on, so forth. So first thing first, look at the norm part. You have an r minus r prime, and you're taking the modulus of that. So this is nothing but this quantity r squared plus r prime squared plus 2rr prime cos theta. I've just written it as the dot product. So let's take out an r squared from the square root. So you get this nasty looking expression out here. So, and I'm going to substitute that in the expression for the potential and pull out the r term because we are integrating with respect to r prime, or we are taking the primed coordinates into consideration. So r really doesn't play significance here. So that's how you get v is 1 over 4 pi epsilon naught r times an all space integral of whatever that's given there. Okay, so one thing again I'd like to emphasize is that we are doing it all space, assuming that outside the domain of interest, rho is 0. You can choose to, however, integrate it within the domain where your charges lie, and that still works fine. It shouldn't be a big deal. Anyway, moving on. Let's do another thing. So notice that you have the square root term and 1 plus x kind of an expression. So this is more like 1 plus x power minus half type of a thing. What you do is you apply the binomial theorem on this, the general binomial theorem, and when you do that, you get something like this. It's a nasty looking expression. And notice that you have an r cap and an r prime. So r prime and r hat, they together give me cos theta term, which is r prime cos theta. So now if you expand this series, you will find out that this, just do a little bit of manipulation here, you find out that you end up with something like this: 1 plus r prime over r power I pi cos theta, where pi is the Legendre polynomial of the ith order, and in place of x, you are using cos theta as the variable. So this is your expression. When you put this back, you get potential as a function of r as this. So notice that you have 1 plus this entire thing. Now, if I break this summation into individual components, you will realize that you have 1 by 4 pi epsilon naught r, rho r prime integrated over the volume with respect to the prime coordinate. That's one term that you get. Now, suppose I take the first term of the summation, r prime over r p1 cos theta, which is simply cos theta. We'll see what happens in the subsequent slide. You'll notice, so these are the poles of a multipole expansion. You have a monopole term, you have a dipole term, you have a quadrupole term. So the monopole term is simply this, 1 over 4 pi epsilon naught r, and all space integral of this guy, rho r prime. So basically what I'm doing is I'm finding the total charge in this charge density configuration. Now, say that it's 0. I have a system of charges because of which the total charge is 0. Then we go for the next level, the dipole configuration. So in the dipole configuration, observe that in this expression, so if I took out the first term, it's going to be r prime over r p1 cos theta. And p1 cos theta is simply cos theta. So since you have an r prime over r, I'm going to take out the r term because it's independent with respect to r prime. So when you do that, you get something like this. You get an r square term, and you have r prime p1 cos theta, which is simply cos theta, and r prime cos theta is r hat dot r prime. So you're left with this. Some people might prefer taking out the r hat outside. So the expression r prime rho r prime. So basically, when you integrate r vector, taking rho as the weight over all space, you get a quantity known as the dipole moment. You are taking the moment of all the individual charges or the charge densities that are there. You're summing the moment, the first order moment associated with these charges. That's one way of looking at the dipole moment associated with this. So this becomes the dipole configuration or the dipole contribution. Sorry, the dipole contribution to the potential. And likewise, you will notice that you get a quadrupole contribution with a 1 over r cube kind of a dependence, and so on and so forth. What you'll notice later on is, as you go down the line or go down the series, the power of r keeps on increasing. So at large distances, the term which dominates is the one where the power of r is the least. So as we know, r square vanishes, 1 over r square vanishes much faster than 1 over r, 1 over r cube vanishes much faster than 1 over r square, so on and so forth. So suppose the monopole term is 0, then at large distances, the dipole term is the prime contributor to the potential, assuming that the dipole itself isn't 0. If the dipole term is 0, then everything falls on the quadrupole term again, and you go on and on. So that way you can predict the kind of dependence that the potential of a system will have at long distances. Will it be 1 over r, 1 over r square, 1 over r cube, and so on. So that is the utility of the multipole expansion, and we get to decide which term contributes to the potential as we go to large distances. So this was the theoretical premise of the multipole expansion. In the next video, we will be talking about, we'll be solving a few problems based on this. So thank you and stay tuned.